Part 3. Hey, this is the Mystery Regen series. I think you guys have been enamored by this little 4-tube Regen from the mid-1920s. And as I do the archaeology on the receiver, I learn more and more. Of course, last time we figured out that this is indeed a Knickerbocker Four from the Keras Electric Company. Now, the Knickerbocker Four, of course, was in a different design, but these are the parts, and I have identified that this is the schematic. So we know we have the right receiver. The more I think about it, this as a kit could be built any way you want to build it, as long as the guy in the radio shop that built it was able to put it into that side table that it was installed in. He could build the receiver any way he wanted. It turned out he built it in a very artsy way, with everything kind of symmetrical looking. Both the front panel and looking down at the receiver, it's very symmetrical. Did he have plans or help? Who knows? It's probably a one-off art piece. I don't think it's a prototype or anything like that. A prototype would be even dirtier than this. It would have even more holes that are repaired or not used. This has a little bit of that, but it looks like it was simply designed to go into the side table. Now, he wasn't completely breaking all the rules. He actually built it in a U shape. So you come into the RF amplifier, the regeneration stage, then you go up to the audio preamp, and then it bends like a U back to the audio output tube. So it's like this shape. That's not a bad way to do an RF system. Is it ideal? No. Ideal is straight line. And if you want to improve, hey, he did this all with plastic. There's no metal. There's no chassis. There's no cabinet. There's not even a front panel that's made of metal. It's not backed up with copper. That's another trick. You can use a plastic front panel, but if you put a copper sheet on the back of the panel, that gives you a metal panel. That's very useful for regenerative receivers. So getting ground on this is tough. And back in the 20s, when they were running everything on batteries, they really didn't believe too much in bypass capacitors. Matter of fact, there is no bypass capacitor. The only capacitor in the whole radio is the Gridley capacitor and the capacitor used for neutralization. It has 0 bypasses, 0 coupling capacitors. So you guys know about mean time between failure, MTBF. Have you ever heard of that? The biggest sin in MBTF is part count. The more parts you have in anything, the more likely it is to fail. So by leaving off all the parts, this receiver has a couple transformers, it's got 4 tubes, 4 sockets, it's got 2 resistors that are wire wound, very, very reliable, 1 resistor in the grid leak, 2 capacitors, that's it. That's the whole receiver. So with such a small part count, this is going to have a very, very long lifetime as a product. I'm going to go through the electronics in this set. It's time to look at the state of the wiring. Now, in the old days, they used to use batteries to power these. Batteries, nice and quiet. You don't have to worry about hum. There's no 117 AC or 220 AC floating around. You just hook up your headphones to this thing and go. We're going to find that when we do hook it up to a real power supply, hum does become an issue. So let's get going. Let's dig into this receiver. First, we have to do a little cosmetic work. We have to do a little cleanup. Then we'll get into the lubrication and the cleaning of contacts, and we'll take it from there. This is the Mystery Regen Receiver, Part 3. Okay, we got some WA1HLR in the background, but I now have the Mystery Regen on the table. The next step is going to be a light cleaning. We've got 100 years of dust. This thing was in a piece of furniture, and that really protected it for many of these years. So we need to do a light cleaning, and it doesn't take strong solvent or something to do this. Just damp it down a little bit and then dry it off. Get rid of the dust. Then carefully, we're going to look at all of the connections. Remember, all of these connections are going through the Formica panels. So they're using some of these as tie points for wires. So there's always a chance of oxidation. So all of those fasteners need to be loosened up, and they need to be retightened, maybe with a little bit of deoxit on them, because we have to make sure we have connectivity. So all of these were fine in 1920, but how good are connections using just a screw terminal as a contact? So I'm going to remove the tubes. We're going to test the tubes in the tester. We're going to lubricate, clean all of the contacts, especially the contacts on the tuning variables. Make sure the micrometric dials work. Let's turn it around. These dials are verniers, so they need to be gone through to make sure the 64-to-1 vernier system works on these dials. I thought at first that these were separate controls, like one for coupling and one for RF tuning, one for regeneration and one for regen tuning. It's not like that. Since everything's coupled together in the Equamatic system, these are simply vernier dials. We want to make sure the rheostats are cleaned and work, and of course this filament on-off switch. I've removed the micrometric dials as well as the homemade templates here. I don't know what these were all about, but it went along with this. Both of these are broken. In other words, it works as a knob okay, in the coarse adjust, but the 64-to-1, no dice, not working at all. These also appear very difficult to take apart. So if I do try to get this thing here, this goes against the front of the panel, and bearing against that is how the vernier works. It's pretty clever, actually. There's no set screw. It's simply this funny looking thing so that goes against the panel, and it causes enough friction that the micromatic part of it would work. It's very clever. You can see it's kind of a spring-loaded looking thing. That is a friction wheel that goes against the panel, and that's what you're bearing against with the vernier. It's very clever. They must have patented that also, but it eliminates the need for a set screw. I just wish it worked. In peering down into this one, I can see that whatever the metal is they used in there, it's got some cracks in it. So I think something has gone bad with the metal they used inside. And of course, they made them difficult to take apart so no one would copy them. That's the way it is. They're just regular knobs now. They don't have the vernier action that they originally had. Okay, I really didn't know what I was doing with this front panel. It was in pretty bad shape, so I actually took some Neverdol to it, which is a really fine polishing compound. I did not get the finish that I wanted in the end. First, I hit it with soap and water, of course. I cheated. I did the knobs with paste wax, and I put a glaze on it, a Rust-Oleum glaze, and that's what gave it this shiny effect on the front panel. Now, the real radio restorers will say I messed up and I screwed up the whole thing, but that's fine. I just wanted it to look good. And I took a shortcut by using the glaze. It's just it's a clear coat. So the 201A, or the UX 201A, or in the case of the Raytheon tubes, ER 201A, they have a 5-volt filament. I could not find the 01A listed on my Precision 912. However, when consulting with the RCA manual, I saw that the Type 26 tube was very similar. The Type 26 has the same pinout, basically the same gain. It's just its filament is 1 volt and not 5 volt. By fooling with the filament, or the B setting, and bringing it to 5 volts, and I can verify that's 5 volts with my meter, it looks like I have the tube lit up correctly. 5.33, that's fine. That's not going to hurt anything. Tube's lit up. and it's reading good. Excellent. Let's put another one in there. Now these tubes are 100 years old. Okay, they're 100-year-old tubes and they're still testing plenty good. It's a nice thing to keep in mind. Let's try this one. Okay, it lit up. It's got a good filament. And let's test it. Okay, this one's not as good as the other one. Its emission isn't as good. One trick you can do with these tubes is to goose the filament temporarily. In other words, light it up a little bit brighter than normal. See what I'm doing here? I'm giving it 6 volts. As you can see, it's coming into the good with the 6 volts. 5 volts again. Didn't do much rejuvenated, I guess. Okay, so one of those ER201s is a little bit light. Maybe we'll use that as the output stage. We'll see. Okay, this is one of the radiotrons, and this is the replacement tube. Testing plenty good. And the last one. This one needs to be wiped off better. Needs to be cleaned. And it's good. So 3 of the 4 tubes are testing plenty good, and 1 is in the yellow. If you increase the filament on the one that's low, of course it tests good. So not bad. 4 tubes in the radio have been bouncing around for 100 years, and 3 out of the 4 are still testing good. So let's talk about what we will expect as far as audio output from a UX201A tube. Now this is a receiving tube. It can be used as detector, amplifier, oscillator, that kind of service. We don't think of it as a power output tube. It has very limited current capability, and its maximum voltage is rated at 135 volts. Now in this receiver, we're running the high voltage at 90 volts on the audio stages, and we're trying to go for 45 volts on the detector. And I have a power supply, which I'll show you in a minute, that I've developed to power the radio. With a receiving tube like a 201A, you could run about 5 milliamps quite easily in Class A. And with 5 milliamps and 100 volts, let's say, that's 500 milliwatts of power. And with a Class A amplifier, we could probably expect to get 100 to 150 milliwatts of audio power out of that tube. Now, 100 to 150 milliwatts doesn't sound like much. Of course, it's plenty for headphones. But to drive a speaker, maybe. So I was looking for a 7,000 to 10,000 ohm input transformer to 8 ohms. I didn't have one of those on hand. I could have used possibly a stereo output type transformer, a push-pull type, and used both sections in series and not using the center tap, and might have been able to approach that. That's possible. But I do have this full-range speaker. It's a vintage. It looks to be about a 7-inch type, maybe an 8-inch type speaker in this box. It has a transformer inside. You can either connect directly for 8 ohms, or when you flick this switch, it puts in a transformer that steps from 600 down to 8. So I've got 600 ohms. I did find this nice transformer, which is 7,500 ohms to 600. So by using this transformer in concert with the transformer that's already in here, I've fashioned a 7,500 ohm to 8 ohm type system. Not ideal. There's going to be some loss and maybe some impedance issues. This will allow me to at least hook a speaker up to our little 4-tube Knickerbocker Four receiver, and maybe we can hear something out. Won't be the highest fidelity, but let's see if the O1A, the UX201A, can produce some audio power. Okay, here's my power supply. And this is a junk box supply built on a piece of wood with a metal front panel. This guy puts out 6 volts at 2 amps regulated. All that is a pair of 7806 regulators in parallel. Nothing fancy. I derived that off a 12.6 volt center tapped filament transformer that's capable of 1.5 amps. So that's 3 amps total capability on this transformer. Conventional full wave rectifier into a capacitor into the regulators. So that's to light up the filaments of the tubes, roughly twice the amount needed to do it with 4 UX201As. Then the high voltage supply, which is 90 volts and 45 volts, derived off a 36 volt transformer. The 36 volt transformer goes into a conventional full wave voltage doubler with a pair of 220 microfarad 100 volt capacitors. That goes into a voltage divider system consisting of a 5K resistor and a 4K resistor, both 10 watts. And on that center tap, I have a additional 22 microfarad capacitor for the 45 volts. That goes to the detector stage. So 6 volts at 2 amps, 45 volts at 10 milliamps with no sag, and 90 volts up to 50 milliamps with no sag. That's plenty of power for this little 4-tube regenerative receiver. So this is where you need the girl that holds her finger up and says, key takeaway. This is a key takeaway. We have 6 volts here. This is going to be going right to the filament circuit of the set. We're going to be adjusting the filaments with the rheostats. Everything's wonderful. When we turn the filaments on, we notice a couple things. First of all, we went out of regulation. We didn't go far out of regulation, but we went out of regulation. And we hear this annoying hum. Basically, these radios were made to be run on batteries. Batteries don't have any hum, they don't have any ripple, and even a clean power supply, or what you think is a clean power supply on the scope, that little bit of ripple is just going to go right into the circuit. There's no proper bypassing. It goes right into the transformers, and they get amplified. The hum gets amplified beautifully. So you have to make sure that your filament voltage is absolutely clean. And that's probably going to take either a lot of capacitance or a regulator. The same goes for the 45 and the 90 volts. They need to be absolutely clean. And my junk box power supply needed a little bit of help to get cleaned up. So here is the proper schematic that shows enough to get this thing settled down. So this improved schematic shows increased values of capacitors and a higher capacity filament transformer that should keep it in regulation. The other thing you could do is use a proper low dropout regulator. Of course, I'm using the parts that you can get for 50 cents, but you can get a $2 regulator that would do a much better job on this. The power inlet connector looked like it was exactly right for an octal tube socket. So I was going to take one of these and file down so I could get this pin to register as the way that the connector goes in properly. I got it all done, and I found out that it wasn't quite octal. The pins were off by just a little bit. This would have made such a slick solution to the power cable. I could have just used a regular power supply inline octal cable, and it would plug right into the back. Not so lucky. So I had to do it the primitive way and use contacts that I rescued out of other sockets and heat shrink, and I was able to buzz out where all of the wires go. You'll notice over here I have this Burgess battery pack, negative bias for the audio stages. And we're talking about the grids of the audio stages. I am applying filament power to the radio. The on-off switch works. You can see the filament went off, filament back on. The two amplifier tubes have additional resistors in their filament lead. Basically, we're putting in 6 volts, so you need to have additional resistance there to lower it to around 5 volts for the tube filaments. So that's what the two wire-wound resistors were on the bottom of the set. The two front tubes are not lit up. They are controlled with the rheostats. The problem is both sides of the rheostat are measuring voltage. So I have voltage here and voltage on the other side. That means that the ground is missing on both of the RF tubes. There's no ground connection, so I have to go underneath and find out what the open circuit is. So we're missing that ground. Let's find out what happened. Up to now, I've been ignoring the solder situation, and I think I found the break. First of all, these solder joints are not looking too healthy in general. I see a lot of oxidation, so I'm probably going to go through all of these solder joints. But I think I see a nice little crack right there. Let's see if I can zoom in. Okay, it's kind of hard to see. Can you see the crack right there? That's the open. Or at least I think that's the open. Let's get some of these solder joints cleaned up. Now, when I'm talking about solder that's 100 years old, solder that's seen aging and oxidation, perhaps bad storage, a lot of moisture, current going through the solder, so there's also some of that going on, perhaps some electrolytic action, you're going to find that the solder has to be replaced, improved, shined up, whatever you want to call it. So this is not the time to be using your little toy solder that you use for your ICs, and it's certainly not the time to be mixing solder like using this non-leaded solder. Let's not use these. This is the time you need to get out your big solder sucker. You need to scrape down the wires that are probably oxidized, clean them up. This is the time where you need to use this thick rosin core solder, the big stuff. You've been waiting to use that, haven't you? And you might even need some flux, okay, some additional flux. And when you're done, you're going to want to clean up those things with alcohol, Q-tips, and so on. The result is going to be renewed, shiny connections all through the system. So I did a pretty good job. It could be better. I had like 10 ohms, 15 ohms, supposed to be completely good soldered connections that were showing high ohms, and some of them open. The radio might have worked, but it certainly wasn't going to work very well with all of those problem solder joints. So you just got to get at it, remove the old solder, add the new solder. You might have to use some flux. There's no way to do this but the right way. So let's get in there. So next I'm going to make the most important measurement that you can make on any 1920s radio. Just about every 1920s radio included audio transformers. And of course, I've been promoting the Keras harmonic audio transformers probably since I began this video series. I say heartbreaking because if one of these primaries or secondaries happens to be open, you're having a bad day, a really bad day. Finding a replacement transformer becomes your quest for the next week, month, year, decade. And I've never seen these before. I imagine they're quite rare. So let's cross fingers and see if we get some kind of a step-up transformer action on these. Step up, step down, something. Okay, let's look at this, this primary. 1.3K. Let's look at its secondary. $8.1K. That's a good transformer. Let's see what the other one is. Just about 1.5K, and the secondary about 9K. Those transformers are both good, fortunately. Boy, that's a close one. So yeah, I've had a couple of these sets come through my hands, over the decades, with blown interstage transformers, a very common problem with these receivers. Okay, I did add a ground post near the antenna post in the back and connected that to the ground bus, so I have made a mod to the receiver already. I've added a ground terminal. The ground terminal goes to this adapter, which goes up to my AM band antenna, which is at the end of that coax. It's an inverted L antenna, about 100 feet long. So this is a proper AM band receive antenna.
The world will ever.
Game 3 is this afternoon at 2:10. Celtics are in Miami tonight, taking on the Heat at 7:30. Bruins beat the Stars 6-3. Bees are back in action Thursday in Florida.
About our sponsor, it's the Burner Launcher.
Let's say you accidentally find yourself caught in the middle of a No Kings protest. Situation you can't easily walk away from. Somebody, locks onto you, some blue-haired lady who's angry.
Whether it's Dak Prescott, CeeDee Lamb, famously Micah Parsons, of course this is going to get dragged out with George Pickens because Jerry either loves it or he can't help himself.
The helpful bacteria. It's a great source of protein.
Okay, so I'm not completely satisfied with this receiver. I feel that the receiver design works and it picks up stations, but they're missing so many bypass capacitors in this thing that it's very difficult to make it work with the external power supplies. I'm sure it would be better behaved with batteries, so I am actually going to fool around with it now. The next video, I'm going to try to add some bypass capacitors, period pieces. They're going to look exactly right. And I'm going to explore why they don't have the tickler coil bypassed. That is the connection between the tickler and the first audio transformer. There's no bypass at all. It's just amazing that it regenerates at all. So some things to do for the next video. I'm not quite done with the receiver yet. It's showing signs of real promise, but I know I can't really demonstrate the equimatic part of it because it's not stable enough for that yet.